This video demonstrates our visual analytics framework for analyzing microblog data at multiple scales of geospatial aggregation. In this video, we will focus on the Boston Marathon bombing event that occurred on April 15th, 2013. On that day, 2 bombs exploded near the finish line during the event at 2:49 p.m. Eastern Standard Time, and this killed 3 and injured 260 people. In order to demonstrate our system from the perspective of real-time analysis, we replay the event and Twitter stream to simulate the interactive analysis process utilizing this streaming data. In this scenario, the emergency response manager selects the injured people, infrastructure damage, safety and security, and response agencies in place, categories for analysis. The manager monitors the microblog stream data based on a sliding window of 30 minutes. He notices an increase in Twitter activity related to disaster and emergency management on the map, with safety and security category taking prominence in certain regions. The major keywords that are trending on the spatial lens include the words bomb, safety, and injure. The manager clicks on the pedal view and discovers a few tweets that mentions that a bomb had just exploded. After allowing the system to run for a little while longer, more clusters begin to appear in neighboring regions, with the safety and security category still being the prominent category that is trending. This can be further observed from the time series views that shows a spike in activity for the safety and security category. The emergency manager hovers over the biggest cluster and finds that the corresponding keywords for this region include bomb and injure. Next, he zooms into this location in order to further explore the underlying microscopic trends for this region. The system provides a smooth transition between the abstract and detailed aggregation levels in order to maintain a visual continuity for the user. Then the manager hovers on several keywords in the lens. The corresponding clusters inside the lens highlight to reflect the selection. The system also allows the manager to interactively adjust the position of different views during the analysis process. As time moves forward, the manager easily discovers from the map view that no tweets are posted near the location of the bombing. This result is to be expected as law enforcement cleared the area immediately surrounding the explosions. The manager also notices that more keywords related to the response agencies in place category appear in the spatial lens, such as SWAT, investigate, and helicopter. This further reflects the priority of the emergency responders' shift from response to investigation after the bombing. In this section, we demonstrate the differences between conventional zooming and the animated transitions of our system. We also highlight the efficiency of using animated transitions in order to avoid abrupt changes where the cluster's relationships to the previous state might not be readily apparent. Here we show the conventional zooming technique and the corresponding behavior of the spatial clustering at different levels. As can be observed, it can be difficult to discern which clusters are merging or splitting when the cluster is comprised of many subclusters. For example, the arrows highlight clusters at each level, and with conventional zooming, it can be difficult for the user to determine whether the two are related. So, they may need to zoom in and out several times in order to identify this relationship. Here we show our proposed animated transition technique with a convex Hall curve surrounding the area where the clusters will appear, slowly fading out the old state and fading in the new state with an intermediary step in between to help maintain the spatial context for the user. The clusters indicated by the arrows have a clear relationship. Thus, we know these subclusters belong to the clusters that was indicated originally.